Welcome back. Hope you're doing well. We've been talking about the geometry of matrices. So far, we've been discussing how 2 by 2 and 3 by 3 linear transformations in particular can be captured by matrices. And each matrix has a way for us to describe what's going on. Namely, the determinant of that matrix is a record of how much the stretches space or the space rather, is stretched by taking a bounded region and putting it through that linear transformation. We've also discussed how certain matrices can rotate space or shear space or flip space or project space, depending on how those matrices are formed. We're going to be talking a little bit more about that here and essentially talk about how matrices can be broken down into their basic core elements of what all they're actually doing by looking at their eigenvalues and eigenvectors. In doing so, we'll be talking about the characteristic polynomial here because that's one of the most common ways for us to solve for what eigenvalues are for a matrix. Let's start with a definition for what these things are. First things first, we're going to be starting with square matrices here, n by n matrices. We're going to say that a number is an eigenvalue of a matrix if we can plug it into this equation and it works. What does this mean? If you take a matrix A, multiply it times a vector V, there exists a vector here, so some non-zero column vector is what we're plugging in for here, for V. If you can get it to be the case that all that happens for that vector, whenever you plug it into the matrix A, what you get out of it is just a scalar multiple of the vector. Geometrically speaking, what does this mean? Plugging in this vector into the matrix did not rotate it, it did not project it, it instead just scaled it. It just made it a scalar multiple of whatever that vector was. If this is the vector, for example, it could have gone to twice its length. It could have also gone in the negative direction. Some scalar multiple of the vector from how it originally came in before the linear transformation and what it was afterwards. Now, this is only for some non-zero column vector. We're not saying that this has to be true for every single vector. Otherwise, we'd be looking at a diagonal matrix. In fact, just a scalar multiple of the identity there. But we are going to say that any vector that has this property for some eigenvalue, lambda, is going to be called an eigenvector of the matrix. In particular, we'll say it belongs to the eigenvalue, lambda, just so that we're not trying to say that those two things are to be thought separately. Really, the two things go together. The lambda that you find here in this equation and this vector v. So some alternate notation here is going to be eigenvalue, eigenvector to be characteristic value and characteristic vector, respectively. Characteristic because we see characteristic equation and things like this playing around in here. Now, we've normally kept the notation of eigenvalue and eigenvector here from the German. When this was developed back in the 19th century, it was a German school that was really at the forefront of what all was kind of going on there. So because of that, we've kind of kept a lot of the German notation from things like that here. But the zero vector, we're not going to consider to be an eigenvector. Notice that in our definition, we excluded zero from our definition of what it means to be an eigenvalue or an eigenvector. We're not going to say the zero vector ever is because it always trivially satisfies this definition. A times zero is always equal to zero, and it doesn't matter what lambda that you put there, right? So it doesn't give us anything interesting to try and talk about the zero vector. We're only going to ask for eigenvectors to be non-zero. Let's go ahead and see some examples here. Let's take the matrix A of 2, 0, 0, 3. First things first, what does this do geometrically? Well, we're taking the standard basis vectors starting from 1, 0 and 0, 1, and we're scaling them in the following ways. In the x direction, we are scaling by a factor of 2 because 1, 0 is going to become 2, 0. And then 0, 1 is going to become 0, 3. We're going to be scaling it by a factor of 3. So it's kind of like we're taking something that is of a square of area 1 and making it a rectangle of area 6. We know it's an area of 6 because that's the determinant of this matrix. Notice, by the way, that we kind of already know what our eigenvectors are, because if we look at what happened to 1, 0, it just scaled by a factor of 2. Indeed, 1, 0 is an eigenvector of this matrix, because if you plug this into 2, 0, 0, 3, if you plug in 1, 0, you get 2, 0. You get the matrix scaled by 2. That is a scalar multiple with the eigenvalue for this eigenvector is 1, 0. And so 0, 1 is also going to be an eigenvector, but we don't have to call it 0, 1 if we don't want to. Notice that any other vector in the span of that vector will do. Namely, 0, negative 2 is also an eigenvector here. and has the same eigenvalue as, say, 0, 1 would. It has an eigenvalue of 3 for this vector 0, -2. So that's the information that we're able to gain from here. Notice that what we mean by geometry, especially in this example, is very apparent. What's happening is we are saying in what directions are we able to scale our vector? Are we scaling in the direction of x by 2? We're scaling in the direction of y by 3. The reason that we're able to just say so very explicitly x and y there is that our eigenvectors are x and y respectively. But what if our eigenvector was something like 1, 1? In that case, we'd be scaling in the direction of 1, 1. We'd be scaling diagonally. And how much would we be scaling by? By the eigenvalue associated to it. So this example kind of is a microcosm of everything that we'll be talking about in today's video. Let's go ahead and see it in another example where we do have to try and pull out some of the stops when it comes to how we scale certain eigenvectors versus eigenvalues. Let's try and find the eigenvectors of these. Well, we can go through and try and do some process of elimination stuff and realize that this one, what this matrix does is it's flipping the x and y directions. So what vector should stay the same? The vector right in the middle. We know that this is going to be reflection across the line y equals x. So the vector 1, 1 makes sense to test, the one where x and y values are the same. Indeed, reflection across the line y equals x does nothing to the vector. That is going to have an eigenvalue of 1. Another good one to test would be the one that is going orthogonal to this line, because that one should just get scaled to be directly underneath the line y equals x. Indeed, if we took this vector 1, -1 and plugged it in, we would get the vector -1, 1. So we would indeed get a flipping with this one. Here we have an eigenvalue of -1. So that's the information that we get there. So we could talk about this one in terms of scaling if we would like to. The y equals x line does not scale at all. Anything along the line y equals -x flips. That's kind of our way of explaining what goes on with this vector. So notice real quick that the vectors v1 and v2 form a basis for R2. This is not always the case. It's not always the case that when you take all the eigenvectors for a particular vector here that you get something that is a basis for R2. But interestingly enough, if you get something like this, take a look at what happens to the matrix of the linear operator L. If we take the linear operator L to just be matrix multiplication by this matrix A, take a look at what its matrix of the function is. This is a diagonal matrix. This is a diagonal matrix, and you can notice that the way that the entries on the diagonal are formed are that these are the eigenvalues associated to each vector. 1 here, this is the eigenvalue for v1, and the reason that it's for v1, and we know it's for v1, is that it's in the first column. Eigenvalue for v2, that's going to be -1, and that is there in the second vector. So we could be also giving the matrix of linear operations by looking for eigenvectors and eigenvalues. If we take a basis with respect to the eigenvectors, then the matrix of this linear operation is going to be diagonal. You know how sometimes it can be a good bit of struggle to try and figure out what the matrix of a linear operator is with respect to a specific basis. Well, if we get to choose a very nice basis, say like a basis of eigenvectors, then our matrix of our matrix of our linear operator is no longer that hard to deal with. It's just a diagonal matrix that's telling us how much we're scaling with respect to v1, how much we're scaling with respect to v2. So in general, we can be doing this for any n by n matrix, not just the examples that we've been seeing here. Let's say that v1 through vn is a non-standard basis for Rn, and let's let B be the matrix of the operator L. The question is, when is this matrix diagonal? Well, it's going to be diagonal if and only if our vectors v1 through vn forming our non-standard basis for Rn are actually the eigenvectors for our original matrix. That's exactly what we saw in that previous example. If this is the case, then what forms those diagonal entries? The eigenvalues associated to each vector. You can kind of see this here, right? The way that you write things in terms of a specific basis is that you write them in terms of what happens to their basis vectors, right? The columns are given by A, B, I, right? These are each of the columns of our matrix of a linear transformation with respect to a non-standard basis here. So our columns are given by AVI. Well, what's happening if VI is an eigenvector? Then this is lambda I times VI, lambda I being the eigenvalue. So that's pretty Pretty cool here. And what's happening is lambda I times vi, that's going to give you exactly what that column is going to look like. We've written this in terms of a linear combination of all of the other vectors inside of this basis. Now, if I is not equal to j, that is, if we are off the diagonal, that automatically means we're going to have a 0 because, as you can see in this linear combination, there is no other component for a vector in the ith column. So if I is not equal to j, then for any of those entries, that scalar in front of vj is going to be 0. So you're going to see a lot of zeros in that column. Now for when I equals j, when you're on the diagonal, the value that you put there is the eigenvalue. And that essentially proves our theorem. It tells us that diagonal entries matrices are exactly ones that we can associate eigenvectors to. In fact, we've got the eigenvalues right there to go through and do it. Vice versa, if you have eigenvectors as your basis, then you can form a diagonal matrix from that. Let's talk about eigenspaces. So far, we've talked about eigenvectors and eigenvalues. But we've noticed, by the way, that whenever you take an eigenvector, the span of anything in that vector, any scalar multiple of that vector, also serves as a very good eigenvector for that element. In particular, whenever you have some sort of space like this, AV equals lambda v, right? If we have some sort of combination of an eigenvector and an eigenvalue combo here, then if I want to go through and try and solve for what all vectors actually solve this equation, then I could go through and try and say, maybe we can start thinking about this as a null space of a particular operator. Well, if we're going to get a null space, we need to make sure everything is equal to 0. So we write lambda as lambda times I. That's just to say that lambda is distributed to each vector, each component, each diagonal entry of the identity there. And then we subtract over a minus lambda I times v. This is an operator. This is an operator for us to look at. Well, this operator, we want to look at the null space at, because now we've moved everything over in this original equation to be equal to 0. So anything associated to an eigenvalue is inside of the null space of an operator. What do we know about the null space of an operator? It's a subspace. A subspace, right? So subspaces are those that are closed under scalar multiplication and addition of those matrices, of those vectors that are inside of there. Conversely, if x is inside the null space of this operator, namely, if it is the case that you get a vector x such that this is true, then you can just move the lambda ix back over, and very soon you get exactly what you have right here, ax equals lambda x. So the eigenvectors of A belonging to the eigenvalue lambda are the non-zero vectors, non-zero because we don't want 0 to be an eigenvector, from the null space of A minus lambda I. So this is what we define to be the eigenspace, is this subspace for the vector space we're working in. As long as this null space is not the 0 vector, otherwise we'd say there's no eigenspace, then it's called the eigenspace of the matrix A, corresponding to the eigenvalue lambda. So how do we find this? How do we go through and do this? How do we get and find eigenspaces for each of these things? Well, given a square matrix A and a scalar lambda, we've essentially walked through many of the different ways that we could be looking for eigenvalues and eigenvectors. So the following statements are equivalent. 1, lambda is an eigenvalue of A. 2, we're able to find a non-trivial vector in the null space, right? Essentially the homogeneous equations set up by the coefficient matrix A minus lambda I has a non-trivial solution, namely a solution that's not just all zeros. We would also get this if the matrix A minus lambda I is singular. We know that a matrix is invertible whenever a determinant is non-zero. So we're looking at the non-invertible matrices when the determinant is 0. And we know that all of these things would be exactly when the null space of this is non-trivial. So we define the determinant of A minus lambda I equals 0 to be a characteristic equation of the matrix A. This one ends up being pretty cool here. If we can find the determinant of the matrix A minus lambda I, set it equal to 0, and solve for our only variable here, which is lambda, then we can find all of the eigenvalues that we're looking for in this matrix. This is called the characteristic equation, helping us find the characteristic scalars and vectors, of course. Eigenvalues lambda of A are roots of the characteristic equation. Roots because we're going to see that there's very likely going to be a polynomial involved here. Associated eigenvectors of A are non-zero solutions of the equation A minus lambda ix equals the 0 vector. So for example, let's take a look at this in the 2 by 2 case, generally with A being a general matrix A, B, C, D, reading left to right. Then the determinant of A minus lambda I, we're about to see, is a polynomial. We're going to have A minus lambda and D minus lambda on the diagonals. And that's because whenever you subtract by lambda I, think about what's happening. You have A, B, C, D minus lambda times the matrix 1, 0, 0, 1. Well, if you multiply a matrix by lambda, every entry is going to be multiplied times lambda. So you're going to have something like this, lambda 0, 0, lambda. If you put all those together, that's exactly what you get right here. Of course, we've got just the straight bars going up and down now because we're taking a look at a determinant of this matrix, which we take here. We know that that's bottom right diagonals minus bottom left diagonals. And after expanding all of that, here is our polynomial, lambda squared minus a plus d in parentheses times lambda, plus, take a look at what this is. This is the determinant of the matrix A, AD minus BC. We've talked about A plus D once, very briefly, in a previous presentation. We called this the trace of A. Recall that the trace of A is the sum of all of the elements along the diagonal of the matrix. So the characteristic equation in 2 by 2 matrices is lambda squared minus the trace of A times lambda plus the determinant of A. Well, we can solve quadratic equations, so we could use this formula to try and figure out what values of lambda that we get. But what happens if we're not working on a 2 by 2 matrix? What if we're looking at a 3 by 3 matrix instead? So solving for the determinant of A minus lambda I, once again, we're going to get a cubic equation this time. Cubic because in taking this determinant, I eventually have to multiply times the bottom right diagonal. So I should have 3 copies of lambda somewhere. And it's going to be a negative lambda cubed because each of these has a negative in front of them. So that's going to give us our coefficient for the first term here. What about our second term here? C1. Well, C1 is going to be what? It's going to be all of those values that you multiply by once you've already determined that you want to be multiplying it by at least 2 copies of lambda here. Well, if we're going and doing the bottom right diagonals, well, then we've got one option. It's A33. We can't be multiplying times this. That's going to give us another copy of lambda and land us in the first term. Then if we want to multiply times, say, the first and third copies of lambda, well, how would we be doing that? We would be going through and figuring out that we need to multiply times A2 there instead, because we've been multiplying lambda, lambda, and A2 as we multiply along this diagonal. And then finally, if we want to get these copies of lambda to be the ones that are multiplied, well, then we have to multiply times A1 as we take the determinant down the diagonal. That is the trace of this matrix. So that's A11 plus A22 plus A33 once you add all of those choices together. C2, a little bit more complicated to try and get the formula of, but it does come from the formula, the way of finding determinants using submatrices. For example, if I know automatically I'm going to multiply times this value of lambda, well, I can't if I'm looking at only one copy of lambda. These two things are ruled out. So I'm going to be taking the determinant of this submatrix here, and that's exactly what you see down here. Same sort of deal if I try and multiply times these other lambdas. I'm going to be multiplying by this submatrix here, which you can find right here. So that's how you can go and find the value of C2 here. And then finally, C3, the one without any powers of lambda at all. In fact, that means you just kind of ignore that these lambdas exist at the very beginning to begin with. Then you're just finding the determinant of your matrix A. So this gives you all of the coefficients that you're looking for your cubic equation now to go through and solve. Now, cubic equations are a little bit trickier to deal with because we don't have a quadratic formula or a neat and easy way to factor every single polynomial that is of degree 3. But let's go ahead and see an example to see what we might have to do with this. Let's take a matrix like this. Let's take A to be 3, 2, 4 on the top, 2, 0, 2 on the second row, and 4, 2, 3 on the third row. Now, first things first, what I'd have to do is try to find and solve the equation of the determinant A minus lambda I equals the 0 vector. Nope, not the 0 vector, just 0. My bad on that. The determinant is always a scalar. Well, I can do that by just taking the determinant of this whenever I plug in minus lambda into any entry of this matrix that is on the diagonal. If I go through and multiply through those things together using the 3 formulas that we had on the previous slide, eventually what I get is, well, first of all, I could start by just trying to take the trace of A. That's going to give me 6. I could also go through and take the determinant of A. That's going to give me, once I go through and do this, I could be expanding by, let's see, maybe expand by the second row here and multiply through on that. And once I do that, I should get a determinant of 8 from my notes here. So if I go and now figure out the other one that came from the specific submatrices that we had before, then the general formula I have for this characteristic equation is negative lambda cubed plus 6 lambda squared plus 15 lambda plus 8 equals 0. I would recommend going through and checking that just real quick. Something to keep in mind in here when you do this formula. Keep in mind that the first and third terms both have minuses in their formula. The reason for the minus in C2 is that when you multiply times one copy of lambda, you get a negative attached out in front of that. So it's going to be negative lambda times the submatrices that you're multiplying by. So the whole negative gets factored out in this formula. So this should be negative lambda cubed plus 6 lambda squared plus 15 lambda plus 8 equals 0. Well, how do we find particular values of lambda? This does not look very factorable to me. Well, we could use what is known as the rational root theorem to at least try and narrow down the number of choices that we have for potential roots. Remember that the rational root theorem says that if you have rational numbers as your coefficients for a polynomial here, then it is the possible roots for this are going to be of the following form: plus or minus a over b, where a is a factor of the constant term, I put those words together, constant term, and b is a factor of the leading coefficient. So, for example, in this case, we're going to have a leading coefficient of -1. That gets absolved by the plus or minus here. So we're just going to have a 1 as our denominator here. And our factors of the constant term are going to be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And essentially what we can do is now just try and do some kind of guided work here. What lambda values would work? Lambda equals 1, for example, doesn't seem like it would work here. We would just be adding the coefficients together if we just plugged in lambda equals 1. What about lambda equals -1? What if we plug in negative minus 1 cubed plus 6 times -1 squared plus 15 times -1 plus 8? Question is, what do I get that's equal to? Well, let's see. -1 cubed is -1 plus, and then a negative out front of that should give us 1. And then plus 6 minus 15 plus 8. All told, that should give us 0, just like we would want. So -1 is a root for this theorem. So -1 is one of my eigenvalues, okay? So then what I do is what? I take negative lambda cubed plus 6 lambda squared plus 15 lambda plus 8 and write it as lambda plus 1 times some quadratic equation. Question is, what is this? Well, I can go through and use the factorization, right, or division by this particular formula in order to do this. If you'll allow me, I'll go ahead and erase the stuff over here. So this way I have a little bit more space to do that. In order to do this, I'm going to do some long polynomial division. I was just teaching this over to some of my junior and senior undergrad students, and they were like, what is this polynomial division that you're talking about? It had just been a while since we had seen it. So we got to talk about it a little bit and see how it kind of all got to shape out together. That was pretty nice. Lambda plus 1 is what we're dividing by this because we are trying to figure out what goes inside of here. Remember that the way that we do this is we say, okay, just take this first term here. How many times can the first term of this little binomial here, of lambda plus 1, how many times can this go into negative lambda cubed? Well, it can go in negative lambda squared times, and we know that because negative lambda squared times lambda is negative lambda cubed. So this is negative lambda squared times this. So this is the goal of this is to try and get rid of this first term. So I go through and multiply negative lambda squared times this entire binomial now, which is negative lambda cubed minus lambda squared, and then I subtract. So this should give me positive 7 lambda squared left over. If I continue this process, then I should get something like 7 lambda squared plus 7 lambda to subtract by over here. So that should give me 8 lambda down here. Plus 8 should give me negative 7 lambda squared plus 7 lambda plus 8. So this is lambda plus 1 times lambda, negative lambda squared plus 7 lambda plus 8. And now I have something that I could go through and factor if I would like. I can now go through either do rational root theorem again and do some division like this one before, or I could write now this is lambda plus 1 times, and I'll go ahead and bring a negative out here, lambda squared minus 7 lambda minus 8. Everything has changed its polarity because I brought a negative outside of that second trinomial there. So then I can write this as negative lambda plus 1 times lambda minus 8 times another factor of lambda plus 1. Notice that I got the same value twice for this characteristic polynomial, the same eigenvalue of lambda equals -1. This would mean, by the way, that we would say that -1 is an eigenvalue of multiplicity 2. Multiplicity 2, let me spell that out. So -1 has multiplicity. There we go, has multiplicity 2. And that's because it is a factor of this particular characteristic equation twice. So after going through multiplying all of that stuff together, we have gathered each of the eigenvalues that we're looking for. -1 happened to take place twice, and then we had 8 as an eigenvalue here. Let me see if I have another blank spot here, because I'd like to use it to try and give another example, so if you would allow me. Let's try and find all eigenvalues of the following matrix A. Here, we're not going to be given the matrix A. Instead, we're just going to be given that A is a 3 by 3 matrix. We're going to be given that we have one eigenvalue of it, that lambda of 1 is 5, that the trace of A is 15, and that the determinant of A is 36. Let's see if we can find all the eigenvalues of this matrix A with this information. How would we do this? There are 3 equations given here, and there are 3 values that we are looking for. What this suggests to me is to attempt to do a system of equations here. Our first equation is given to us, lambda 1 plus 0 lambda 2 plus 0 lambda 3, if we're calling our eigenvalues by lambda sub I. This is equal to 5. What's the trace of A? The trace of A is lambda 1 plus lambda 2 plus lambda 3, because we're just adding all of the eigenvalues that are given here. Interesting, right? Why is this true? Well, the trace is something that is not going to, let me check something real quick here. Okay, thank you for allowing me to check my notes for a little bit. The sum of the eigenvalues actually comes from how we write the characteristic equation itself. Remember that our way of writing this characteristic equation was negative lambda cubed plus the trace of A times lambda squared minus, we had some kind of value here, times lambda plus the determinant of A. There's some neat things here that are useful from our algebra class, not just algebra in terms of undergrad algebra, but sometimes this is a formula that could be discussed in maybe an advanced level of high school math as well. And it might be interesting if you're in school or anything like this and teaching to go through with your students at some point. The sum of all of the roots of this, multiplicity included, the sum of all roots of this given equation is equal to the trace of A. Is equal to whatever this coefficient is. Technically, it's going to be divided by this value right here. So keep that in mind as well. And then we're going to have, or rather the negative of that value. And then we're going to have that the product, lambda 1, lambda 2, lambda 3, is equal to the determinant of A, rather the constant coefficient here. Now, this one, I believe, might actually have a negative in it. I didn't include that in my notes here, but this one might have a negative on it. So this might be worth checking. Let me go ahead and do that real quick. All right, it does end up being positive. And the reason for this that is pretty interesting here, to me at least, is that we could write this polynomial, once it's all factored out, as lambda times the first value that we get, lambda times 1, lambda times 2, lambda times 3. And in this case, since we have a negative out front, it's going to be a negative out here as well. So it's going to be written in this sort of form. Think of this as like the fully factored form of this cubic value. Well, if I want to find the lambda squared term, what am I going to do? I'm going to choose which factors have 2 factors of lambda in them. I don't have much choice here. It's lambda, lambda, and negative lambda 3 for one, lambda, lambda, and negative lambda 2 for another, and then lambda, lambda, and negative lambda 1 for the third. Adding those together, I should get the negative lambda 1 minus lambda 2 minus lambda 3 with a negative out front, which makes this a positive value right out here. And then for the constant term, I only have one choice in each of my factors, and that's going to be lambda 1, lambda 2, lambda 3. There are 4 lambdas total. There are 4 negatives total. That was the thing that I was missing and kind of going through it in my head. This should be a positive value right here. So with this system of equations, neat little thing here, we can still figure out three equations with three unknowns to solve for each of these eigenvalues here in this setup for this type of problem. So now, even without having the matrix, having things like the determinant and the trace of our matrix can give us everything that we need. Well, as long as we have one eigenvalue to help us get started. That gives us the three equations we need with the three unknowns. Pretty neat little example there. I just wanted to kind of give that before I continue moving on. All right, so we've talked a little bit about how we can find the eigenvalues of a 3 by 3 matrix using its characteristic equation. In general, and for any theorem for n by n matrices, what you're going to get from taking this determinant is itself a polynomial. If we're working with an n by n matrix, what we get is a polynomial. But the solution to at least certain terms of this polynomial is going to be that getting the coefficient here in front of the lambda of n minus 1, say the kind of the not the leading coefficient, but the one right behind, that coefficient is going to either be the trace or the negative trace of your matrix that you're working with. And at the very end, your product of roots is always going to be the determinant of A. So this is a neat little theorem that tells us that we can go through and find characteristic polynomials for any of these things. If we're patient enough, the rational root theorem can get us all the way through. This is known as the characteristic polynomial. Corollary, any n by n matrix has at most n eigenvalues because there's at most n solutions to this equation here. Let's go ahead and see just another example here to get working with this characteristic equation, this time nice and typed out for us so that we can see this here. Characteristic equation of 2, 1, 1, 2. I could go through and try and check out, okay, does this eigenvector work? How much does it scale by? And things like this. Or I could use this characteristic equation now to try and help me out. I could subtract by lambda on the diagonal entries and then solve the characteristic equation given by 2 minus lambda squared minus 1. When I do that, I'm going to get lambda squared minus 4 lambda, and then I think my plus 3. So whenever I solve that one, I'm going to get 2 lambda values of 1 and 3 respectively. Now the question is, now that I have that information, how am I going to find the eigenvector associated to it? We've done a lot of work to find eigenvalues. What about eigenvectors? Well, remember that eigenvectors are the ones that solve this equation right here. A minus lambda I times that vector, this is the eigenvector associated to lambda, is equal to 0. This is the eigenvector for lambda. In this case, we're making lambda equal to 1. We're looking at, since we know lambda equals 1 is an eigenvalue, we're asking what vectors work for this one. So we're trying to find the solution to this particular equation. 1, 1, 1, 1 times xy equals 0. Well, if I'm going to try and find a general solution for this, remember, I don't just want to try and plug in x and y and get that there's 0, for example. That doesn't help me very much. I want to find a general solution for x and y. So what I could do here is do some system of equations, some row reducing here, if I would like to try and find the values of x and y that work here. If I do that, then I'm going to figure out that x plus y needs to equal 0 following row reduction. If I do that, then I see that any value that works for x and y is going to be one where y equals negative x. So if I plug in that x is 1, y must be negative 1. The general solution for this can be written as negative t, or t times the vector negative 1, 1. So negative 1, 1 is a good eigenvector for me to choose that's associated to this eigenvalue of 1. The corresponding eigenspace for this is the line spanned by V1. Eigenspace meaning the subspace that contains this vector, right? Kind of the smallest subspace that contains it, so hence the span. Well, that was for one of the eigenvectors. What about the other one? What about for the eigenvalue of 3? At this point, we get a different matrix here that we can now also go through and do some row reduction on. If we do that, we get that this with the eigenvalue of lambda 3, then we get that the solutions xy must be on the line x minus y equals 0, or the line y equals x. So that's going to be spanned by the vector 1, 1. So the vector v2, 1, 1 is going to be our eigenvector corresponding to the eigenvalue of 3. So the corresponding eigenspace is going to be the line spanned by that vector. What that did for us is this. Let's connect this all back to the geometry we were talking about at the very beginning. First things first. 2 eigenvalues. We've got 1 and 3 as our eigenvalues here. The second thing is that the eigenspaces of A associated to each of those are like we discussed above. There's 2 lines going on here. One is going off in this direction, Here's the vector 1, 1. And then we're going to have the other one that's going off in this direction, negative 1, 1. So those are our two eigenvectors here, and the eigenspaces are going to be the things that are spanned by those. First things first, I can notice that those eigenvectors actually span R2. So I can describe how any vector works by seeing how it works with these eigenvectors. That's the neat thing. I can describe how any vector, once plugged in to the linear transformation, just given by this matrix multiplication, plugging in any vector here, because that vector can be written as a linear combination of v1 and v2, that means that I can describe what happens to that vector when it gets plugged into A. Let's see how we can describe it down here. Geometrically, the mapping from x to ax is a stretch by a factor of 3 away from the line x plus y equals 0. Again, that's the line y equals negative x. So the map x to ax is a stretch by a factor of 3 away from the line x plus y equals 0. Okay, why did we choose this line? I thought there were two lines going on here. I thought there was a line y equals x going on as well, right? And that was the one that had the eigenvalue of 3. So what are we talking about here? Well, think of it this way. If you started with the vector 1, 1, what would you be doing? Well, the vector 1, 1, once I plug it into this vector, we know that 1, 1 is the one associated to the eigenvalue of 3. And so that's going to get extended. This one's going to extend after being plugged through A, extend by a factor of 3. Well, wouldn't you agree that that vector is indeed, tracing here, the orthogonal direction away from the line x plus y equals 0? That's exactly what's being meant here. That vector is meant to capture the component of a vector that is orthogonal, going farther away from the line x plus y equals 0. It's actually extending it by a factor of 3 in that orthogonal direction. Now, if we started with the vector negative 1, 1, for example, well, that one has an eigenvalue of 1. There's nothing to describe. Anything on this line is going to stay exactly the same because for that particular value, a of negative 1, 1 is just 1 times negative 1, 1. It stays the exact same. So we can be describing any vector here first as a linear combination of how it works with negative 1, 1 and 1, 1, and then say for the part of it that's going negative 1, 1, it's staying the same. For the part of it that's going in the direction of 1, 1, it's getting scaled by a factor of 3. So that's exactly what's being meant by this bullet point here. Let's do another example, this time with 3 by 3 matrices. Let's see the characteristic equation for this one real quick. We just subtract by lambda on everything here, and we can expand out either by using our formulas from before, or by just deciding to take the determinant using submatrices, for example. For this one in particular, submatrices seems like a good idea because you just have an empty bottom row here, so expanding by the third row seems like a good idea. If I do that, I'm going to get this equation to solve for. I'm going to get lambda 1 equals 0 and lambda sub 2 equals 2. Notice, by the way, that lambda sub 2 is of multiplicity 2. Very neat there. Okay, well, now let's see what happens when I try and go through and solve for each of these. Well, I have 0 as an eigenvalue. What does it mean to have 0 as an eigenvalue? That I'm getting a non-trivial solution to this equation. A times x equals 0 times x. That's exactly this equation here. It's the homogeneous equation. So we're looking for a non-trivial solution to this equation given here. We don't have to subtract by anything because it's just ax equals lambda x, and lambda x already equals 0 here. So we go ahead and reduce to row echelon form, and we get a solution for this in terms of x, y, and z. Doing this, we get exactly this setup, x plus y equals 0 and z equals 0. Thus, we get a general solution for this in terms of our variables. So we're going to get negative t0, or the vector negative 1, 1, 0, being the spanning vector for this space, all being multiplied times a constant of t in order to get us along the line spanned by that vector. So this is our eigenvector, and the corresponding eigenspace is the line spanned by v1. But keep in mind that our previous eigenvalue had a multiplicity of 2. What that means is that it's possible that we don't just have one eigenvector there. We could still have one eigenvector, but it's possible that we have two non-trivial or linearly independent vectors there that work for us. This could be an eigenspace dimension of 2, but we don't know that from the outset. We have to go through and check. So let's see what happens whenever I'm working with the eigenvalue of 2 on this one. Well, I'm going to be solving a minus lambda I times x equals 0. Here, lambda is 2, so this is the matrix that I'm going to get from that. Going through and doing row reduction on this, take a look. I have 2 0 rows, which means I'm going to have 2 non-pivot columns. So y and z are going to be free variables for me. I can just go through and solve this for something in terms of x. X is going to be equal to y minus z. So if I make y a parameter, something like t, if I make z a parameter, something like s, then x is going to be t minus s. So that's going to give me a two-dimensional eigenspace, one spanned by 1, 1, 0, one spanned by negative 1, 0, 1, once I separate the t's from the s's here. So we have 2 eigenvectors associated with this one eigenvalue of 2. The corresponding eigenspace is the plane spanned by v2 and v3. So what does this mean in our summary? The matrix A has 2 eigenvalues, 0 and 2. The eigenvalue of 0 is simple. What we mean by simple here is that it has a corresponding eigenspace of a line. Eigenvalue 2 is of multiplicity 2. The corresponding eigenspace is a plane. And then we have that once we go through and check, the eigenvectors indeed do form a basis of R3. Well, first of all, the eigenspaces have to be going in opposite directions, because otherwise you would not be able to actually solve the equation ax equals lambda x for 2 different values of x. So that means that whenever you have eigenvectors belonging to different eigenvalues, they must be linearly independent from each other. So one eigenspace goes this way, one eigenspace goes this way. One plane is 2 dimensions, a line is another dimension. That's 3 dimensions in total. Another reason to see that these eigenvectors form a basis. But geometrically, what's going on here? The map from x to ax is the projection onto the plane span of v2, v3. Let's just stop right there. Projection onto the plane v2, v3. What's happening here? Why is v1 not mentioned here? Remember that v1 is the eigenvector associated to the eigenvalue of 0. And what happens when you plug in v1? It pancakes. It just gets projected. The component of a vector in the direction of v1 is going to get pancaked into a particular plane. And that plane is going to be the one, well, of the other vectors that were given here, v2 and v3. And what happens when you project something what happens when you have a vector that's in the plane? Well, the component of a vector in the plane is going to get scaled by the eigenvalue of 2. It's going to get scaled by 2, thanks to it having an eigenvalue of 2. So this is a way of geometrically giving us an understanding of what happens with this matrix. So even though this matrix, when we look at it, seems to spit nothing of this at us, we can use eigenvalues and eigenvectors to help us understand the geometry of this operator. So let's spell that out one more time, just very quickly when it comes to this geometry stuff here. So first, v1, looking at this eigenspace. So let's look at the eigenspace of v1. Anything that's happening in this space, right? Only things that exist in this space are going to be copies or scalar multiples of v1. That's going to be what this eigenspace is. And what happens when I plug in a times r of v1? Well, the r is going to be able to come outside thanks to how matrix multiplication works. And we know that a v1 is going to be, since v1 is the eigenvalue, has an eigenvalue of 0, this is going to be r times lambda 1 v1, which in this case is just going to be the 0 vector. So everything here is just going to get flattened. If I wanted to rewrite it, though, it would be lambda 1 times r v1. In the case that, for example, it was non-zero for our eigenvalue here, we would just be getting that it is a times anything inside of this eigenspace is lambda times anything inside of that eigenspace. This is also, by the way, a proof that any other vector in the eigenspace of this vector would work as an eigenvector for it. Eigenspace of v2. Eigenspace of v2. We have 2 choices here because we have 2 vectors to be working with. v2 and v3 is really how I should have been saying it. The eigenspace of v2 and v3 are going to be any linear combination of elements inside of v2 and v3. Well, if I write what a is going to be when I multiply that through, a of alpha v2 plus beta v3. Once I go through and write that out, I can multiply the matrix A inside and bring the alpha and beta being the alpha and beta outside and the A inside. So this can be rewritten in terms of this, alpha AV2 plus beta AV3. Now, AV2 and AV3, since V2 and V3 are eigenvectors, this is going to be alpha of lambda 2 V2 plus beta lambda 2 V3. Lambda 2 just meaning the second eigenvalue, the one associated to this eigenspace. Finally, I can go ahead and factor the lambda 2 out, and I'm left with the original vector that I had over here. So any vector inside of this eigenspace is also an eigenvector for us over here. But that should do it for today's video. All we've done today is talk about the geometry of these matrices in terms of their eigenvectors, eigenvalues, and their eigenspaces. Thank you so much. Have a wonderful day.